Hello, Detlef.
Hi, Adi.
This is a kind of a reunion here between, of course, you and me, but not only. Also because everything what we kind of did together, and it's like quite differentiated and complicated. Yeah, Detlef, I prepared today publications. Most of them we made together as a little surprise, and I put in some gemstones and materials that are important for all these publications, and I'll go quickly through them just to make a little summary of what we worked together.
What do you mean by most? Everything I see here we did together.
Beside this one, where I got the name from.
You got the name from, but...
I didn't do it.
No, but you found the sample.
Okay, but I have to...
Sampling is part of it. Okay,
no, but that's not my
that.
publication. Okay, but one of the pieces here was the starting momentum, remember?
Yeah, of course, but it is everything we did so far. Let's put it this way.
Oh, okay. Do you want to work warm with me?
Well, there might be a lot of stories to come in the near future.
Super, great. Yes!
This is actually the stone which I requested from you in 1999 when we met in Eric Rose's microprobe lab.
A diamond, right?
It's a diamond, and I just saw that you are the only one who could provide us something for fundamental studies with the laser system, right?
Oh.
Eric did with the microprobe all the majors, and I was looking for traces. And diamond is the hardest material to ablate. And then you remember what we talked about?
About major elements and trace elements.
Yeah, but you told me actually they are called diamonds because they don't have a lot of traces, right? And you offered me that all the other gemstones which you are working with, they have the entire variety of traces, etc.
Wow, you have a good memory. Right? That's true.
Great. And then 2002, the first, what I say, firewalk exercise we did at the time, right? This was...
Firework exercise?
Yeah.
Ah, yeah, right. Always come somebody and then you have to drop everything and take the emergency.
5:30, Adi Peretti. We are there at 10 o'clock, okay? This is the typical way of analyzing it with you. Has never changed over time.
Clean, huh?
But you remember, the major part when we talked about laser ablation was really cool because we explained we can do the entire traces, we can do the entire periodic table. But then actually it was, Eric did a great job on major elements with the microprobe, very important. And then we used some of the elements as an internal standard to do the quantification of trace elements, right? And most important in mass spectrometry are the light isotopes, and if you really look, that is lithium, boron, beryllium. And then we tweaked the machine actually to the low mass region. The high mass region was easy, and then started step by step by step, and you see beautifully when we analyzed the rim, we found then the enriched beryllium. Remember that?
Oh, yeah, right.
Is it right? Is it not right? Are the counts okay? Etc. etc. So
that
the first validation.
That was a walk on the cliff.
Exactly, and you've been extremely well in explaining what's the story behind it.
Oh, yeah.
Completely crazy.
Next driver cannot open the car, and all the bags and everything, underpants and everything is in Bangkok, and I'm here in Colombo, and all my books I want to give for the symposium tomorrow. Everything is in Bangkok, cannot come here. Is that crazy or no? Huh?
Sure.
Ties, suits, shirts, socks, shoes for the meeting, everything gone. The insurance said they don't want to pay, and the taxi driver, he says my bag was too big, he cannot open behind anymore, it's my fault. So now I have to send a lawyer to make them problem. Is that funny life or no? It's terrible. This morning I come from Switzerland, fly from Bangkok to Colombo, and what's happening? Everything gone. All the bags, also digital camera gone, geological instruments gone, everything gone. I eat Swiss chocolate, at least we have Swiss chocolate.
Then we can show.
and wait for the toothbrush they bring me from the room service. And tomorrow about 100 people are coming, you know. Can change the whole talk, everything.
Terrible.
From University of Zurich for his master's thesis focused on tectonics and metamorphism in the Alps, and is acknowledged by both the British and German Gemological Associations. Invite Dr. Karabi to deliver his lecture.
Thank you very much.
Today, I want to speak on something that for us in a laboratory was a very hot topic at the end of last year, because since about 2004 we have in our laboratory a laser equipment, laser-induced plasma spectrometer, which we constructed ourselves. So it's a prototype which has been specially designed to detect low concentration of beryllium. Since about 2 years I'm working on a book on inclusions, and we try always to capture inclusions as many different types as possible. So at the end of the last year, the inclusion pictures in the sapphire dramatically changed. I was very excited about it because I had the feeling I can make some additions to my book with spectacular new type of inclusions. Suddenly I was running with one of those sapphires to my laser instrument and measuring it, and it had a substantial amount of beryllium. So we did not exactly know why there was beryllium in the sapphire, but we made a note on the internet. At the same time, I was publishing my book, but the taxi driver couldn't open the drawer anymore, so all my bags and everything stayed in Bangkok, and this is fresh suit from Sri Lanka. And then this books actually is our research from 2003 to 2005, edited, and as a summary.
And that was 2003, it's almost 20 years ago, if you look back. Now we know actually how to ablate that diamond. We don't need that anymore. So
This is a diamond with a cross in it. It's a nice symbol for how we met and worked.
These elements and defects and so on is very, very complicated. So we have this for the scientist, and we make a very short new name because it's not the same like other treatments, it's completely new. We make a short new name for this product so that the people nice, very nice.
ก็บอกเดี๋ยวก็ได้ทำงานถ่ายรูปกับอีที่6 คนเนี่ยถ่ายรูปเป็นแค่ประกาศคุณบอกให้เราทำงานดูว่าคนทำงาน
Was welcome to our wonder world of minerals, and I was wondering how is your new life as an emeritus professor of the University of Bern, where you were so incredibly active, and now you're still making mineralogy?
How do you feel? What are you going to do in the future? And I like to answer all these questions in the public, that you don't have to talk to me about these subjects.
Actually, no. Actually, no. I gave completely up continuing my original profession, and I changed my life, absolutely.
So I have mixed feelings. The last week I cleaned my office after spending 35 years in the same office, and I threw away the PhD thesis of my PhD students. I threw away the master thesis. I threw away all habilitations I ever evaluated.
I'm cleaning horse stables and I'm working with horses. This is my life, and you see it easily on the tie I'm wearing. I have no longer a tie with crystals on it.
So you're proud about your new profession?
Yes, sure.
I play with the horses. I catch mice in the garden. I work on the weed in the garden. And I'm open for any challenge. So if somebody has any challenge for me, just contact me. I'm available.
So if you do as good with horses as you did with minerals, then you probably must win very quickly an award in a race somewhere with the horses. I will die to watch it.
Okay.
But let's revisit together a little bit our joint past. Also, we have been working together on minerals and new minerals and fantastic stuff for a couple of decades. And I was wondering, because you were always testing students for master thesis, passing in mineralogy, crystallography, everything, whether today I can reverse it and test you.
Okay.
So I'm gonna a little bit test you out, and probably you will reverse it during the talk, and you're gonna test me later. It looks like a huge disaster, but there is a huge systematic in it, and after we are through with it, everybody can make his master thesis.
Okay.
Okay, so I have questions for you.
Look at this. Right?
Oh yeah, that's this one here. What is that? Remember that?
Well, I'm a chemist. You are the mineralogist and
Yeah,
geologist.
but I have to test
That's
you
a
also
tourmaline, and it's beautiful actually. I was
Paraíba.
always
Paraíba.
dreaming. Yeah,
Paraíba.
Paraíba. I was always. I just knew actually the watermelon and the black ones, right? But this one, yeah, here this was very spectacular. First of all, the light elements, yeah, the light elements, and then the beautiful trace element that we did imaging. You remember that? We really went across and could really show the crystal structure with high resolution. It was really amazing if you look into that.
You made profiles.
Exactly.
Profiles.
Exactly.
And then we made profiles like 81 points over it, and every point you have to measure how long it takes, like 2-3 minutes.
Yeah.
And then 81 to 2-3 minutes.
1 point is something like 90 seconds, 1.5 minutes.
1.5 minute times 80 is like 3 hours. One crystal.
Well,
I mean pure measuring time, but not like the interruptions and then the standardization.
We never got interrupted, so that means we really worked continuously. But today we would not just simply go here across. Today we could actually image the entire mineral, because we can place now 200 laser pulses. These are 81, right? We can place 200 laser pulses within 1 second.
Wow.
So that means, and every signal is completely resolved from the others. So that means the development over time is just dramatic. So that means next challenge is waiting for us. Right. Now that was really very, very good. And what I liked actually is the story behind it, right? It was Mozambique, Paraíba.
Yeah, right. So
where is it coming from? Right?
Exactly, they were found new in Mozambique and put into the market as Brazilian tourmalines, and then we could make this study to separate them out. This one is a Paraíba tourmaline, and its matrix comes from Brazil. Okay, it gets heavy lifting now. We change the topic.
Okay.
Hold it.
Okay.
How heavy is it?
Let's say it's very heavy.
No kilo, 2, 3, 4.
I would say 3 kilo.
Yeah.
So it's an epidote?
No.
Okay, then
Look
it's
at here.
yeah. Okay, no. Then it's a tourmaline, a shell, a black.
Yes, exactly.
Black tourmaline.
So that was just an introduction into the tourmalines, and then I give you something else, and then you notice a difference.
Yes.
What?
Expansive color of tourmaline.
Remember the name? That's unfair. It's a gemological background.
Yes.
I cannot test. It's a Paraíba tourmaline from Brazil.
Yeah, Paraíba. Yes, I remember the name.
So
yes.
how is it colored? Which element? That one counts for passing the exam. Remember the cup? Oh, I gave you already the answer.
It could be copper.
If it's 100%.
Yeah, okay.
Yeah, and the general type of tourmaline, because we have tourmaline is a group,
Yes.
and we have minerals inside the group.
Yes.
Do you remember a few of them?
Most common elbaite, dravite, and so on. Yes.
Yeah, elbaite, dravite, lidicoatite, and so on. I mean, sometimes we look tourmaline when we cut them through, right?
Yes.
And then we see that they are zoned. You said it already for the garnet that is zoned.
Yes.
And here, you see this?
Beautiful.
This is one crystal we cut, tak, 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 tak,
Yes.
and this is the center. It's a guesswork, but speculation. But
Yes,
can do it.
I would immediately say it starts like an elbaite with lithium and manganese 3+, giving the pink color, and then the iron increases, and then you get the greenish parts of.
And lidicoatite.
Yeah, could always be, but you
we
cannot.
don't
You cannot.
Yeah. So elbaite, dravite, lidicoatite, rosmanite,
Yes.
all these are single minerals that
Yes.
are considered as end members.
Yes.
And all of them have different qualities and so on. And so it's so difficult to say it. So we say only the group, right? Okay, so this is an andesine from Mongolia that has been treated. One is natural.
Exactly. Now, do you remember this story?
The andesine was a huge hype in the industry, and they had groups fighting with each other whether they had treatments or not. We wanted to thank everybody of the group, from Guenther, from our company, our lab, and the gemologists in Asia and Switzerland that have helped us to solve a little mystery. And the product of this mystery is this book. And in this book, nobody in the world could find out how to distinguish a gemstone, whether it was treated or not, and particularly this one coming from Tibet. What they did with the gemstone is they diffuse copper into the stone. And so a large number of these stones appeared in the market, and what it did, it kicked out the gemstone from America, from Oregon. They say you sell it fake, and actually it's natural and not natural, so it's a huge mess.
Treated
If
this
you go today
stone
on the internet,
here,
you type
which
in
looks
andesine,
yellow or white or pastel yellow, and andesine oligoclase feldspar from Mongolia, and make out with copper diffusion into it something like this, a beautiful orangey red vibrant stone, and that it was sold in Tucson for a very high price, and they said it's from Congo. Remember? They just took a mine that nobody ever can go, and actually it was supposed to be from Tibet at the end of the day.
and it started all very funny with this gemstone. When I went to Tibet, the guys showed me a mine, and this mine was fake.
Can you read what's on the table?
The danger area.
Like for Tibet.
Yeah. Just do at morning.
早上早晚转
Morning.
早上转最好
You move that, then good luck for Tibet.
好，扎西德勒，扎西德勒。这边也是，你跟我走吧。
Mr. Lee say you can follow him. He will introduce you where can find.
原来挖的大大小小的好多坑，好多洞的，挖的那种探坑啊，有时候就是挖出来这些东西啊，下面太大的石头我没办法给推平了。
Mr. Lee say the mine is finished, so the area is flat.
都是这样的石头比较多，下面大的很多，就推平了，没用了。那石头里面没有东西。
I can stop it for a moment.
我们过这边来。
The difficult is that Mr. Lee say the big stone is difficult to mine.
哎呀，我挖吧，
好难挖
挖这个大的。
He say you can
挖这个大的。
practice this one.
挖这个。
Dig around this one.
挖这个大的。
Why they are here?
Right?
How he knows they are here? How he know that they are here?
佢問你點知道嗰度有？
我們這個活幹多了。
Experience, because they have mining much.
因為什麼？它有那個砾石的層。
He said mostly they find the Anderson at the around the big stone. It's a layer.
I tell you today it have rain.
佢話今日佢講過話今日會落雨。佢之前佢 check 過網頁嗰啲咧，都話今日會呢幾日會唔好咁好天。
那邊還有，你也可以這麼來，然後你幹累了，我們的工人也可以來，你也可以看看我們的工人怎麼樣工作的。
We can go to other mine to study. The layer, Mr. Lee say.
Top layer, huh?
最頂層。
Never have inside here.
佢問有冇曾經喺裏邊揾到喎？
沒有。
冇啊。
No.
Nothing.
Here, no.
絕對沒有過。
Here, no.
沒有。
要啊。
好啊。
好啊。Wait a moment.
還有我啊。
Get cold.
你自己的，佢自己的。
Yourself? You have keep yourself?
I have next one.
佢有第二個啊。Second one?
Yeah, you can close camera now.
Okay.
It's for you. That is the cliff of the deposit going down to the river. They didn't mine anything, and I insisted to go and check the cross section for fallen down andesite. That's the final proof that they were really in a stratigraphic horizon. And we'll find it. So they're working there for me, and I come now. It seems that we find the andesite in the hard rock. And I will take sample now to confirm that these are andesite. This is 100% proof this is natural. We'll take this sample out.
小心啊！哎，不行不行不行！
So it's a little reportage about the mine trip in here, and it shows how they put for me stones in and how they made artificial mine. So this is the first report about an artificial mine in the world.
And then we had to differentiate them from the ones from Oregon, because the Oregon miners were quite pissed. They were not happy about somebody coming in, treat stones and sell them in Tucson and blow them away with more nicer colors. There was an ongoing issue, and then And then I came to you and we were thinking about making isotopes for heavier elements.
Well done. That was the starting point. I mean, I remember that very well, that we started with laser ablation. We analyzed all the trace elements as we did in the previous studies. Then all of a sudden was insufficient, right?
Mm-hmm.
Prediction was maybe treated with copper, maybe treated at 1000 whatever degree to diffuse that in. And our prediction was maybe we can measure the difference between 63, 65 mass difference and a diffusion into the center. And well, it describes very nicely this huge machine where we measured all the details.
The femto machine.
It was the femto, but it was also the multi-collector ICP mass spectrometer, and that was really a challenge. But we found something in addition.
You got the only machine? You got the only one in the world? Or
No,
number 3, number 4? Or
that is
10 machines in the world? Or?
We had a good combination with the laser, but there have been many before that. But nobody predicted actually that we could measure diffusion coefficients into a mineral. And you remember that the trace elements as an impurity was a constant lithium signal. You remember that?
Yeah.
It was something like 4 or 5 ppm, which was continuously going through. So that was the first indication. And then the gas spectrometry. Decided first actually that we lost the argon, so that was the first indication, and then we found the reality in terms of fluid inclusion, and that brought me back actually, because that was the reason why I got hired to Zurich to analyze fluid inclusion. That was my first story. That's the reason what we built the instrument for.
Look, something I'll tell you. You told me that you are only interested in horses anymore. I don't believe you. You know why? You have here a symbol of a crystal on your jacket. So you took a tie and this one. And if I'm not mistaken, this is an award from the Russian Academy of Science?
No, but it's appetite.
Appetite crystal structure. Because I witnessed you get like the highest awards in the world of mineralogy from the Russian Academy of Science. First one?
No.
Which one was it? I witnessed it during your...
No. I'm a honorary member of the Russian Mineralogical Association.
Yeah, that's what I seen. They made you an honorary member. The Russians know how to check crystal structure and everything, and so that is, it's not easy to get that one.
Yeah,
I know that one.
I threw away all the crystals, several thousands which I collected and on which I did the structure, and I had a virtual tear in my eye, and it was not easy. It really was not easy. So I learned that emeritieren means to throw out of the honors. I think it's a good thing, give the young generation a chance, let things go on. Evolution would not work without that. If the old ones would survive forever, everything would stay the same. We would probably run around with fur coats and with axes and hammers and so on. No, it should change, it's fine.
That was in 2008. And recently, geopolitical situation changed the game. And as a vice president of Russian Mineralogical Society, I'm proud to announce that this year, Council of our society elected Thomas as its honorary member. So Thomas now will be in good company with such scientists as Guenther, Anne Carnot, Goldschmidt, Denard, William Breck, IUI, and by the way also Yoga Warden. So this is our Russian response to the current situation. And let's wait and see what Americans will tell.
Well, what should I say? I'm speechless, of course. I would suggest we move now to the mineralogy collection.
Okay, one thing I wanted to show you, it's quite impressive and important also for gemology is these two. One is, as you see, the color, right, red. I don't have to ask you, that's easy. And this one is blue, and they have.
I have to guess again. No.
Yeah.
I would say if you show me that, it's probably a cobalt spinel
from Vietnam.
And this is a classical red.
Chromium.
spinel color comes from chromium. And it's surprising again, because we were having the barrels and we had the chromium color making the crystals green.
And this one?
And this one is red.
From chromium. One time it makes green, one time it makes red?
Yes, exactly.
Why?
It's the environment, it's the crystal field environment of the crystal structure which is responsible that the chromium has different transitions, and so it can be responsible for the greenish color. And as in the rubies, this is almost a ruby similar color, right?
Yeah, yeah.
So it can also make crystals red.
Oh, yeah. So if somebody says chromium makes red, it's wrong.
It's wrong, yes.
Yeah. So we make this as a landmark, because sometimes in geological history it matters to create landmark analysis where we have fixed points, where we put a lot of energy in, and when we are defining something very detailed. First here it was a new gem mineral where we had found a new chemistry and a new structure for something that has never been there in the knowledge of the world. Here we had to go and measure an element that nobody at that time could measure to prove that there was a treatment with the beryllium and interpret it correctly.
They could measure it, but they could not measure it in a multi-element mode together with all the other elements. So that means light and light trace and major element. That was not possible. Exactly.
And then here we have another example of authenticity for treatment using heavy element isotopes.
Yeah, but this is the best example. If you just see, why do you need a laser at 193 nanometer? Why do you need an image to a small space of 10 micrometer? Just to really breach into some of the fluid inclusions, to open it under controlled conditions. And that was actually the original idea why we built this laser system in there. Quartz you cannot tackle at 193 with other wavelengths. This is a perfect example.
It expanded later also into origin of new gems, where we found like the nickel element was something new in a deposit which are totally different than the others. Yeah. And then fantastic gemstones, treatments for the industry.
Do you know the story here, what we did? With the nickel?
No.
Cannot be.
What?
Well, mass spectrometry is easy and complicated. And then was the question, 44 calcium, 16 oxygen. This is 60 nickel. Well, did you measure 61? Did you measure 62? So we screened the entire isotopes actually to really validate that it's real nickel.
Ah, I didn't know that.
These are 8 ppm and 5 to 8 ppm. That was really a story behind it. So we really looked into that it's analytically correct, and then we could bring up the entire interpretation.
This is a ruby from Guenther, a new discovery that we worked on.
All these statements are more or less wrong. For example, cordierite, as an example, you call it also as a gemstone iolite, because it's ion.
Used by the Vikings.
The violet, yes.
To navigate the stars.
Exactly.
Why? How did they do it? How? Why did the Vikings use cordierite, iolite to navigate the north?
Well, it's the extremely strong pleochroism of the crystals, which is color dependent, which is direction dependent, and it depends on the polarization of the light. And so you can actually determine whether you have light coming from the north or you have...
They looked with the iolite.
Yes.
And when there is a lot of light, they see dichroism. And when there is less light, they see less dichroism. So they could find out in the foggy north where the sun is.
Yes, yes.
And then they knew with the time and the place of the sun, they could navigate.
Yeah, yeah.
And they needed the iolite for that.
Yes.
And that was their secret trick. That was the enigma machine of the Second World War, was the iolite of the Vikings. And we could have invented it with our knowledge.
Yeah.
Right?
Sure.
All right.
Yeah. But let me just come back to the color problem again. We were talking about the the cordierite, because iolite, it's bluish, lilac, bluish, and so on. It's two-valent iron. Two-valent iron is also responsible for the green color in the olivine, and two-valent iron is for the baby blue color
in the aquamarine.
Yeah. So actually, the color alone is extremely dangerous for determining what kind of element is it. Yes.
Besides that, we have idichromatic and allochromatic with major element and trace elements, and then we can have both allochromatic and idichromatic and put in traces, and then we can think this is a general mineral formula. Call it, actually they have also traces in it, making it so it's all open. That's why we needed to go also together away from all this thing, you know, into more deep analysis. So we are gonna looking this here, 1, 2, and let me see which one, and this one. This belong together, and this one. So there is a very unique story and beauty story in this. Something is all different, same, and something else is different.
Yes.
It's your turn again.
Okay.
If you want to pass the test.
Yes.
Give you 90 scores, it's okay. But we're probably going to make 100 total, you know.
Okay.
All right.
So first of all, from a mineralogical point of view, these 4 specimens belong to the same mineral species. The species is a beryl.
Correct.
And all the varieties in color which we observe here, the green coming from the chromium, the blue coming from the iron, or the pinkish color, which is actually mainly caused by 3-valent manganese, traces of 3-valent manganese. So we call this different color varieties, and so this would be called aquamarine or something like that. This is a typical, probably even Colombian type, or...
Correct. What? Emerald.
Emerald, yes. Right. And this one is probably a morganite.
Correct.
A pinkish type of beryl. It could be also something else, like a pizzottite or something like that. But the only reason that I can say it's probably not a pizzottite, because even you could not afford a pizzottite of this size.
How do you know?
I don't know. Simple assumption.
Right. We leave it.
I have never seen such a large pizzottite.
Actually, when I got it, I hoped it's a pezzottite.
Yes.
And then I tested its cesium concentration, and it was just at the border and not one. And I was like, no way.
Is it from Afghanistan?
No, the same like where the pezzottite come from, the same mine.
Okay.
That is so sad.
Yeah.
So what was the difference between this and pezzottite? Actually, we did publish it.
Yes.
Right?
Here, remember that one? Pezzottite?
Yeah, that was a new mineral and a new gem mineral. So we had actually worked on treatments, new minerals, completely new minerals, not known, identify them where we needed your laser ablation analysis, because they had light elements like beryllium, and that only your machines can do. And then we had even to use isotopes of copper.
Right, but step by step.
Right.
This one was really cool. But if you look into all the other stories, right, you always promise this is completely new, not known, never ever discovered. Okay, every story started with the same story. We are unique, so that's the reason why we actually analyzed it. But this was one of the pezzottite discovery together with the structure. It was really a beautiful stone.
The chemistry of the pezzottite is much more complex. So a normal beryl has no lithium in the structure, or let's say not significant concentrations of lithium. And the other thing is the beryl structure has always these open channels, and these open channels may carry sodium, potassium, water, and in the special case of pezzottite, we have extremely high cesium concentrations, and cesium is a large ions which plugs the channels in this structure, exactly. So for this reason, the cesium leads to some specific ordering patterns in the structure, which means it no longer follows the classical hexagonal structure of, let's say, the morganite with exactly, more or less exactly the same color, but it reduces the symmetry, it becomes rhombohedral, and the cell is much larger than the unit cell of a common, let's say, beryl type mineral.
Superstructure.
Yes, yes. So the basic, you're absolutely right, the basic structure, if you just look at it, a fast glance on it, then you think, oh, it's the same as a beryl. But if you look at more detail, then you see, oh, there's some ordering pattern between the lithium and the cesium in different positions in the structure, which reduces the symmetry and is unique for the pezzottite.
Can I tell a little story?
Yes.
That is pezzottite that I cut from this material.
Remember that very well, and luckily we got a smaller stone because we could really place it in the laser ablation chamber, and then we analyzed it. That's the original.
We broke it up from this one.
Yeah. I was always scared to break something because we have
pezzottite crystal.
Yeah, we have the stone floor where I had sometimes really fear if we dropped them actually, that they would break.
But this was, get more than one piece back.
Right. Exactly.
But there is a little event behind it, right?
Yeah.
So this crystal here, there were 3 groups working on it.
Yes.
To identify the mineral.
Yes.
And then they joined from California University and American institution and so on, because nobody knew what it is when it first came, because they have a higher refractive index than beryl.
Yes.
They didn't know what to do. So was the hunt out who can determine this crystal structure.
Yes.
This is painite. The painite with rubies on the top, peppered.
Yeah.
The world record, one of the biggest. It played a role. And the painite was from Mr. Payne from Mogok, and at the time they made the mineral, and for his name, the crystal structure was done with instrument from that time, you know. And
right.
They couldn't measure boron.
They couldn't measure boron, and that's where we stepped in again. So that means for the light elements we've been not really beatable, and the method is somehow a key part really then to make the structure. But Armbruster contributed. Remember that?
Yeah.
With the best instrument in the world.
Yeah,
on his side, right?
Yeah, right. So he had this multi-channel measurement machine that took all the reflexes in one shot rather than scanning it through. He got it all like illuminated a skyline of reflections and then see them all at the same time. So he could really figure it out, and then this crystal structure was wrong, published before. I take this piece, take a piece off and went to you in Bern, and there was this huge machine with multi-channel detector X-ray thing that you had for zeolite research, got sponsored from, I guess, the oil industry or something, or from the university. And then you were working there, and I came, and then you joined me and measured this, and how long did it take you to measure that crystal structure?
I forgot.
I know. Almost a month.
Yeah,
because it had the superstructure has so weak peaks you couldn't get it out quickly.
Yes.
The others didn't have it.
Yes.
So they were getting a necessity to join with us.
Yes.
So that's why we gave this mineral later with the chemical formula of cesium, beryllium, lithium, aluminium, silicate, the space group R3C and everything, and applied to the National Mineralogical Association for a new mineral, together with a group from Caltech University and so on. Yes. Everybody joined with Professor Hawthorne, you know, is in your league and so on, and we applied it and got the name pezzottite for, and so we discovered the new mineral.
Yes,
right?
Yeah, correct.
So I decided to make this book as a
cooking book how to make a new mineral.
Yes.
Step 1, step 2, step 3. Because
Yes.
I was like, if somebody else wants to go through the same suffering like we went, they need a cooking book. And I found out that the references is everywhere in the world as how to make a new mineral. Yeah, and that was the name of our article. The challenge of the identification of a new mineral species, example Bezotite. And all the steps exactly how we applied it to the IMA, I followed up and showed how we did it, how it is happening, and what you have to do so you can get all these different things out that you need to make a new mineral, right? And then we have all the machines from everything was necessary. We had the chemical analysis with electron microprobe and laser ablation, and we had yours with the crystallography started, and we have to all put together. Then you have to compare it to all the other minerals existing in the world, right? And then with the Bezotite crystals and everything, and what is different than the others, and all that, and we applied, and it got approved.
Yes.
Wasn't that crazy?
Yeah, absolutely.
Absolutely crazy.
Absolutely.
And to make a new mineral, you need the space group.
Yes.
And only our group could do it.
Yeah.
We were the one.
Yeah, yeah.
I don't say the others were wrong.
No,
I just
no,
say
no,
we
no.
were the one.
Yeah,
but
yeah,
they
yeah.
needed us,
Yeah.
and so we did that. That was quite interesting.
There is a funny story in the background.
Oh. I never heard it?
Probably not. Probably not. We actually have solved the structure of this mineral Bezotite, showing the lower symmetry, showing the distribution of cesium and lithium in the structure and so on. But I was never 100% content with the quality of the data I collected on this crystal. As you said, I had to collect the data for months to see the very weak reflections.
I remember very well.
And then, of course, the quality of these weak reflections was not so excellent that we could determine the thermal motion of these positions of the lithium and so on. So I was not so happy with it. I could publish, let's say, the outer shape of the structure, but I was not willing to publish the numeric values of all the coordinates
or the position of every atom.
Position of every atom. I could have done it, but I was not happy because sometimes there were inconsistencies about the thermal motion of the atom. So I said, okay, the quality is not good enough. I can do it later, measuring half a year when I have a machine available or something like that. So then finally, somebody noticed, oh, the structure has not been published yet in details with all the coordinates.
A blood droplet.
Yes, and they published a structure in a quality which was less than 10% of the quality of a structure I had on my desk.
And you didn't publish it?
No.
These are is this one of the regrets in life?
No.
It's just science.
No, it's okay.
It happens.
Yes.
Yeah. I have also a lot of these files that somebody else, I found out, and a half year later somebody published it.
Sure.
Sometimes it makes like this.
No.
All right.
Of course, if I would had to review that paper, which I had never the opportunity to do,
you would have found it out.
I would have said, no, this is not the quality you can publish in an international scientific journal.
Oh.
But okay, that's it.
Now I know more about it.
Yeah.
So you revisit, you get a new crystal structure. So this paper we made was like the definition of bainite, but you don't change the name because it was originally giving for the discovery and everything.
It was not important, but the structure came for us. But this was in particular one of the best examples why we work as analytical chemists in geology. If you make the wrong age determination and come up and say the Earth is 8 billion years, okay, everyone knows that you are completely nuts, all right? If you would provide here the wrong boron concentration, you would never come up with a corrected crystal structure, right? So that means you have really the
internal
proof.
control.
You have the proof in the structure family that the contributions of all the trace elements, or even here major elements, they make sense or they don't make sense, right? They're wrong or they're right. And certain of these applications been really cool proof of concept and cool proof of the accuracy of the method. Yeah, cool.
You remember this one?
This is your achidolite.
Yeah, this one is yokakidolite, comes from Burma, and was found the second time as a locality, and we redid this one. And this one is the same like this, but cut, yokakidolite, that also appears in colorless materials.
Well, the story was extremely difficult in the beginning. Rare earth element pattern, known, natural, yes, and then is the crystal structure really the crystal structure as described, right? Mm-hmm. And we contributed beautifully all the light elements to really make the structure complete, and then we could revise the entire crystal structure. This was amazing because here you catched us in saying this has never been described before. Mm-hmm. And here you said all the specialists been wrong.
And
they've been wrong because we corrected it. So that means you kept to your story, so that we never analyzed something for the garbage bag. But garbage bag is a good name.
And there was this one mineral.
Yes.
Which I think
carries your name.
If you look all this, which one is your most favorite project?
All of them have been really very exciting. All of a sudden, what a surprise, the peritite. Well, in particular, actually, when we knew that this one is named after you, the entire crew behind the curtain, we didn't let you know. We've been all very happy because for all the contributions you did, you deserve that.
Oh, thank you so much. That's very nice.
Violent event in the universe, a supernova.
In just a few seconds, supernovas create more energy than our sun ever will.
Within a couple seconds after beginning to make iron, a star explodes in a supernova. So think about that when you're holding one of your iron frying pans. The iron killed a star in just a few seconds. Dangerous stuff.
And a lot of the people that have thought it was great had supernova moments.
Would you care to join me in watching the supernova?
Supernova!
It is a once-in-a-lifetime experience. Supernova.
As a gemologist in the market, you're not looking for a bargain of a stone or try to buy it cheap or later sell it or that. That's not the point. The point is you look for something undiscovered. Something that they overlooked or something that came new up, have new aspects, and you need your knowledge from all these visits from before, and then you are eventually going to discover something totally new. And very often it ends up by checking the microworld, the inclusion, and what's inside the stone. And there we can make huge discoveries. And in Mogok, it was this crystal here. It was a phenakite. And they came on the table and I was there checking the stones and looking with the loupe and looking inside. And suddenly I discovered this needle, these orange needles, very fantastic, beautiful needles. And they were there, but not in many stones, only in a few. And I knew this is something new. It's different, I never have seen it before. So was it maybe a new mineral? Because if you really want to know what it is, you have to go through a very lengthy process of identification. You have to be ready for it. And that is the passion that comes in. This is the passion of the gemologist. And keep on going, and then you have to follow it up. You have to go through it. You have to follow this crystal and break it out and analyze it at the specialized laboratories, and then maybe comes a new mineral out. You know, a new mineral, an invention of nature, of chemistry and of structure, something that was never there, an invention of nature. Maybe it's a new combination of atoms that has huge implication for technology. It was produced at one point in time in the history of the world, and it was hiding in this mineral, and it might be destroyed or never discovered, and nobody ever would have known that this combination of atoms is possible. And then you are there and you're rescuing this formula, this structure. These needles turned out to be a new mineral composed of rare earth elements, silicium and boron. A combination of light elements and heavy elements. And the rare earth elements contained europium, samarium, yttrium and very, very rare elements.
So first of all, I should mention I received during my active time, let's say 20 minerals per month and people were saying it's something new. You have to look at it in more detail. Yeah. And we put it on our machines and it was well-known material.
Aragonite, calcite.
Boring.
It was great fun to work on that actually because not known, damn small. Isn't that here?
Inside,
right?
Yeah.
So, and then all of a sudden, there is a new mineral.
Yeah, you are considered as one of the pioneers in chemical element detection. What is the special method you are using, and where's this machine?
We use laser beams to analyze micro regions of hard minerals with mass spectrometry at the back end for detection, and therefore we are able to have extremely low detection limits, so we get traces and ultra traces. We have driven this method over years, more or less 20 years now, and I would say we made significant contributions to the international community. We have analyzed this new mineral, and we found the ultra trace elements which you cannot detect by other techniques. Mass spectrometry is the most sensitive part, and in particular the rare earth elements and the light elements like lithium, beryllium and boron were really of significance for the crystal structure.
You're called by many a super specialist. Can you describe us in what field?
Well, I'm a mineralogical crystallographer, and that means we are exploring the atomic structure of minerals, and we are interested in the forces which are responsible for the properties of the materials of the natural minerals.
We heard that there is also a mineral named after you. What mineral is that, and what is its name, and how do you feel about it when there are minerals named after you?
Okay. So armbrusterite is also a sheet silicate, and it was actually named after me because I was supporting collaborative research with the East European countries, and it was found on the Kola Peninsula in Russia. And as a thank you from the Russian scientists for this collaboration, they named this mineral after me, and I invited me to see the mine where the mineral comes from.
So how does it feel when the mineral...
It makes everybody proud to become immortal.
When a new mineral is discovered and you are in the expert group decoding it, how does it feel?
You would not see me jump very high, but it's exciting. But I like more actually that we could provide Adi Peretti somehow an award actually, which he deserves for his continuous contribution to the field. And here I'm extremely proud that my name is on it. So this brings us into history, right? Because in 100 years, these mineral structures will not change.
Yeah,
other papers will be forgotten, but this is actually...
You know that peritteite now is not only a mineral, now it's a mineral group, because I discovered bauxite, and both peritteite and bauxite are now a member of the peritteite group minerals.
Very nice.
Yeah.
This is very nice. Well, the story started, right? And this is highly memorable because, look, this entire team, right? It's not a single person, not a single technique which actually provided all the details. It's always a team, it's always expertise from... It's like a soccer team, you know? We have a good goalie, we have a good forward, and all the others played well and scored.
I can say how much I appreciated to know that I have friends at universities as a backup, because as a lab you can't have all the machines and you can't have all these interactions and so on, and it always contributes so much to our success that we have reliability and finding not only scientists but friends
and consultants and people that go the extra mile for something more than just a business relation.
What did you figure out about the...
A special thing about describing the new mineral peritite was it's the world record for us in describing a new mineral. Last year, in 2014 in August, we received a sample from Adi Peretti, and now we are end of August 2015. We already received the galley proofs of the manuscript, which will be printed in November. So I already contributed to the description of about 50 new minerals, and in all cases it was much, much slower. And you should consider that the International Commission takes about a quarter of a year, in our case from December up to June. So this is 6 months until we receive this decision. And during this time we couldn't do anything on this project. And then in June we did some additional measurements, submitted everything already in July, and now it's in print and will be out on the market in November, December. So this is a unique opportunity to show how a team can improve if it cooperates for a long time and everybody knows the weaknesses and the power of the others, and it's coordinating itself, and at the end this is the result, new world record.
All these years, all these things that we found out and so on would have absolutely not been possible to have without all the Swiss universities backing up us so much, and all the many meetings we have where we meet the strategies together and all the time, you know, with the whole group, right?
That was really cool, yeah.
Yeah, so it's a nice heritage, and that you say you still want to work with me after all my turbulences that I brought in your group and so on is a big compliment. And
three requests.
Okay.
Follow the European watch, call at the appropriate time, and give us a notice in advance. Well, Adi, in 10 years' time we will have another table with new books. Is that the deal?
Actually, we're working right now on a project.
Yes.
We have the amber project, where we just measured a while ago the amber with the calcite veins inside. Hello, Christoph.
Hi, Adi.
Can I come in?
Yes, of course. Could you please wear a lab coat and covers for your shoes?
This one?
Yes.
This yours?
Yes, this.
All right. You're afraid of bringing the dust from the road in? They can hurt the machine?
Not the machine, but can interfere with the analysis.
How with the analysis?
Please send on the sticky tape.
Yeah.
And then you can come in.
All right. Hey, super great.
Hi, nice to see you back.
How are you?
I'm fine. You?
Yeah, it's great. Great to be back here in this crazy laboratory, man.
Yeah.
Here, this one. This is the one we are going to measure, and then you need to go with the laser, and I want to know the chemical composition of the carbonate replacing the lizard. And we have this amber from different mines.
Right, and the manganese is one of these elements which really...
We found an element, right? The lizard comes to the surface of the amber, comes out, you know, so we can actually go there with the laser, right? We don't have to go and burn some amber.
Yeah.
Oh, yeah. It's good. It comes very nice to the surface, and you can go there with the laser. It's okay.
Yeah.
Yeah. All right. Yeah. You measure only 50 microns, right? A very small spot. We will not see any damage, right?
You will see a small damage, but a very small damage, and for the size of the lizard, it's almost invisible.
With the naked eye, we cannot see it, right?
We just need a free surface from the calcite in the lizard.
Exactly. So the lizard is exposed to the surface and is internally replaced by calcite, and you can measure and reach it with the laser on the surface. You will see it there, over there. You can help me with the laser ablation machine. This one I'm better than you. It's my job, you know. I'm the professional microscope guy, not you.
Well, it's not a fingerprint at the moment, but the preliminary indication we have is really that one element gives us a perfect match, manganese. And I think as an indicator and the first proof of concept, it should be known to the general public. And maybe there are some more elements we find in the near future, or we test it on some other samples and then we will definitely validate it. But the first indication was really impressive, that it's almost identical. It's not a real fingerprint, but it's a one element indication. And maybe we have to repeat and add certain more samples to it, but at least the proof of concept, I would say, as we have seen it in other applications, is also done here. Now, what's your interpretation if you hear manganese?
So good. So you saw this, right? The structure, and now we are gonna give it to you. It's all yours. And so you will put an argon stream to it, or is it helium?
I will use a helium stream because the ablation process works much better in helium.
You mean the ablation, like the laser picks up structure and elements from the substrate we want to measure, it makes them become like a gas?
Yes, exactly. The laser evaporates a small part of the sample.
Of the laser that goes bye-bye.
Exactly.
Yeah. And it goes in?
And only on the surface.
Oh, okay.
And the process of creating this gas or aerosol is much better in helium compared to argon. And that's why I use helium for the ablation.
Why it's expensive, helium?
Yes, it's expensive, but also the other instruments are expensive, so it's not the only part.
Okay, great. So,
yeah.
Wow, now it gets into the machine, huh?
Yeah.
Mamma mia. Okay, so you have to focus exactly to the spot, huh?
Exactly on the sample surface.
So you see it there, right?
And to the spot where we want to measure the composition.
Yeah.
Now,
this is like less than a hundredth of a millimeter, huh?
Yes.
Yeah, and so that's the spot how we're going to measure. So this spot we're going to get 50 different elements out in chemical composition.
Yes. But we have
all the rare earth elements, manganese, titanium, iron.
Yes, the whole periodic table from lithium to uranium.
Everything.
Everything.
So this is a new generation that does it all.
No, it's not a new generation.
But a good generation.
It's one of the best instruments we have.
Okay. Well, I'm honored for that one. You know, we want to get the best data out.
Yes.
So we will know the composition of rare earth elements and so on, down to 1 parts per million, right? ppm.
Even lower.
So,
even in the
0.1.
So even in the parts per billion range.
Wow! That's amazing, huh?
Yeah.
Hiya. So we see everything. Whatever happened in this vein at that time, with that went in, and something was contaminated. Something happened in the environment. It will be in the vein, and we'll pick it up like forensic.
Yes.
Geological forensic study.
Yeah, that's what I like.
Yeah. All right, I can't wait to see it.
So,
is it sharp?
It's ready, so we need to turn on the laser. Okay, now the laser is running, but it's still blocked with a shutter, so that the laser starts to shoot on the sample when we are ready with the measurement.
Oh, yeah. So we look at that over there?
Yes, exactly.
All right, okay.
So you can take a seat over here.
Oh, thank you so much. Yeah, right. Wow. So these are the atomic numbers of the elements.
Magnesium isotope.
Magnesium isotope 25.
Exactly.
And this is 44 is the
calcium.
Calcium isotope. Not 44.
That's what we use for the internal standardization of the quantification.
Yeah, because calcite is calcium carbonate, and then we know the matrix, so we can make it by definition to 100% CaCO3.
Yes, exactly.
And then we have the 56 is
iron.
It's isotope, and 139 is a very heavy one. Is that manganese or something?
That's lanthanum.
Lanthanum. That's a rare earth element.
Yes, exactly. And then also cerium 140.
Lanthanum and cerium, huh?
Yes.
Two rare earth elements.
Yes.
Normally, rare earth elements like to replace calcium, right?
Yeah.
So that's why we expect them in the crystal in generally, because they have theoretically can go in. Huh?
But you missed out the most important element for our analysis.
Manganese.
That's 55. That's manganese.
Ah, right.
And we saw that the calcite has the largest spread from different areas in the manganese concentration.
For our study.
For our study.
Yeah,
exactly.
This is just like the lizard now, you know.
Yeah.
Yeah. Because we want to measure the veins, and from the vein we want to know which mine it is.
Yes.
And when we have a lizard in the amber and we don't know where it comes from, we measure the element in the lizard and compare to the veins of the mine, and then we know, it's this mine, or this mine. So this laser ablation is not only measuring the trace elements of the calcite itself, we apply it to become a criminological tool to find out where the amber came from which mine.
Yeah.
So it's a control for me, because the miner find the amber, and then I have to control them somehow to be sure,
Yeah.
Yeah, we had 3 mining areas, two stories to do. We had to separate all the calcite veins from the 3 different mining areas that are far away from each other. Mm-hmm. And secondly, we wanted to compare that with lizards to see whether unknown samples would show that or not when they are important. So the first part, we really saw the difference between the Tinlin mine, Tanai mine and Kamti mine, who are very far away from each other. From our geological work, we see that one of the mines of the 3 mining areas, and Kamti has many, many smaller mines, this cluster from Kamti is actually different from Tinlin and Tanai, but Tinlin and Tanai could not be separated, but the Kamti could. And the Kamti geologically is pelagic, is deep ocean, while the others are shallow and platform. And so we could see the difference from the deeper to the platform, and the deeper ocean normally have these manganese nodules. They're very well known for ocean floor formation. So these manganese nodules most probably came into the contact with the rocks, or integrated or contributing to the general setup of the material. And when the veins go through, they pick up the trace elements that are in the rock, and in the Kamti area they would pick up manganese, for example, while in the others it's less possible because there are no manganese coming in from the geological setting to begin with. The comparison to the lizards, or whether the application has a kind of an breakthrough momentum, has to be seen, because we have to expand it to more samples. It's always like that,
Right.
Gemology, high-tech analysis, identifying materials and put them in the right place is like an interaction between people in the field, people bringing the material, bringing up the questions, and then the cooperation with the university that have high investments and have the overlook on the best machines.
Well, you're absolutely right, but for interdisciplinary work, the first proof of principle, you have to know each other. That's clear. Okay. Second is you have to find common sense, and somehow also you have to like each other, otherwise you wouldn't do these kind of adventures, right? But then I would really say we had more. We had a really cool team, because I remember that all the samples, went from here to Bern to all the different other places, and then we started to discuss the results, and that made it really cool. And from all the groups, it was not important who is the first author or whatever.
Yeah.
For us, it was important, do we get out a good story? And that was really nice. And of course, you need this individual instrumentation. And Thomas is a high specialist, well known in the world. We have Guenther, also well known, and I guess actually we are also a little bit known for laser ablation in the world. Dedicated development and then finding really cool applications, and I found it always very nice. These are I would say geology is a perfect application for what we are doing, because you need to know what individual element is in all these beautiful natural samples.
You ready to open the shutter? 2, 1, go. Yeah, now you can see the signal rising.
Rising up.
That's a signal from the calcite.
And here is the base.
Yeah. So in the end we will subtract the base from the signal
This one
to get the true signal from the sample.
Right. And the manganese will be here like 50. The yellow one is the manganese?
Manganese,
is the
iron,
highest. Yeah.
Also some magnesium and a little bit of the rare earth elements.
Yeah, they're a little bit there, huh?
Yes, they are.
Wow, give me a break. So the rare earth elements were moving around in the deposit in the veins, huh?
Yeah.
Here is the base and here's the real signal.
Yeah.
Up to here. That difference here, we can calculate the chemical composition.
Yeah.
Yeah. ppms.
ppm, ppb.
ppb, ppm.
Yeah.
Percent. Depends.
Yeah, we can. We can go up to 40% from calcium in the calcite.
All right. So this one is in percentages already.
Yeah.
And then here, this is logarithmic.
This is a logarithmic scale.
So always 10 times more.
Yeah.
From here to here, 10 times more, 10 times more. So manganese is maybe 10, 20 times less than this?
Here it's just like 5 times less in the signal, but the signal does not directly correlates to the concentration. So we have also to take into account the abundance of the isotopes, and then also the sensitivity for different elements in the ICP-MS. And
because every element has different isotopes, like the manganese have 55 and have 56.
No, manganese just has one isotope.
Only one.
So we have 100% of 55.
But the calcium has many isotopes.
And there you have got just 2% of the isotope 44.
That's why 2%. It looks almost the same like manganese, but it's much, much higher.
Yeah.
So it will be like 10 times, almost 50 times higher in reality when you correct for the isotopes.
Yeah.
Okay.
Okay, then you can also stop the button. Yeah. And
so now the signal will come down a little bit with delay, huh?
Yeah.
And that mountain, you will extrapolate them from the years. You're gonna calibrate against the standard. Something we had measured before, and we know the exact composition, and you measure it also, and then you make a ratio of it.
Yeah.
And then after that, you make for mass corrections and all quantification stuff, and then you're calculating it up to the matrix of 99% calcite.
Yes, we assume 100% calcite, but this induces just a small error of 1%.
All right.
But the uncertainty of the measurement, we say if it's within plus minus 10%, we are happy with the results, and so we can accept this 1% deviation for the quantification.
So this is one sample, it takes about 10 minutes to do?
2 minutes.
2 minutes, but for the preparation it takes like 2 hours?
Yeah.
Standardization takes 3 hours, and if the standard, or 1 hour, half an hour?
I mean, it depends on what you all want to measure.
Yeah,
but preparation of everything took, of the instrument took 2 hours, then measuring the standards 45 minutes, and then 8 to 10 minutes for each sample, and the more sample you have, the longer the analysis.
So we measured already 49 samples, so we were working for 4 or 5 days non-stop.
Yeah.
Exactly. Only to get the data.
Yeah.
And then you have to go back in the office and calculate everything. It's another 2 weeks of work.
Yeah.
So we have 3 to 4 weeks measurement to do.
Yeah.
And then the high-tech machines and everything included. It's quite a big project, huh?
Yeah, it's a big one, but it's also a very interesting one.
Oh.
No?
Thank you for the compliment. Actually, we have seen the manganese is quite high, huh?
Yeah.
That's amazing, how the manganese.
Yeah, that was also surprising for me. I did not expect that.
Yeah, okay, there are samples from the ocean, so it really might mean something. So I hope, that this signal will be different in the different mines, because they are in different environments. Some are shallow water, some are deep water. And the deep water, I would expect higher manganese. You have the manganese nodules in the deep water by hydrothermal events, and you don't have it in the shelf where we have the other mines.
Yeah.
So when the veins go to the rock, they will see this manganese and will remobilize it into the vein. So the one amber that is in the deeper ocean will see this manganese in the veins, while the one in the delta or at the lower or the shallow platform will not see it, you know. So we have these different mines. So that would be actually fantastic. So I can't wait to see the results when they come out with all the comparison of all the data. So it's super.
Yeah, me too. I will let you know.
You took your time and you worked hard and everything, and it's such a hard life to be a scientist, and I appreciate it so much.
Yeah,
see you.
Thank you.
Again, huh?
See you.
Yeah. Yeah, so Detlef, you know, we have this project, and I brought you here one more time to show you the samples. This one is from a mine in Burma near the jade occurrences. It harbors amber in it, and at the same time it has veins from a later event that go through. Here you see it, the amber itself, it came from the rock, and you see again the veins that go through, not only to the rock, also go and penetrate through the amber. And it's often that the miners have to collect lots and lots of amber and polish them, and after that they find something interesting. And in that process, all the stones from different areas go to a cutting center and get mixed up, and the exact origin may be still known or maybe not. And because the three mining areas are far away from each other, and they have different ages from 70 million up to eventually 110 million, it's very important that we know exactly from which mine they come, so we know the ages. And with the ages, it's very important. So we started this with you, and that's like the samples, you know, like we measure them. These are the samples that go into your machine. Well, this is too big. That we break small ones that are all from different mines, collect them. We have like 50 measured so far. You see the little bit amber, and then here a little bit of carbonate. And then we were measuring that a couple of weeks ago with one of your assistants or PhD candidates, and I think you brought me some news today.
Well, nicely explained what we did actually. Yeah, Christoph Neef analyzed the samples. We discussed what the trace element patterns could and should be. So we put the element menu together, and he ablated a couple of samples. And the good news is that at least for one pair, actually, we match very well in terms of manganese. The other element pattern are not as indicative as the manganese, but we have to, let's say, figure out, is that a true fingerprint, or finding different couples, pairs, and then analyzing it. But what I think actually it is extremely well justified and validated on those sample. Could be a completely new concept, and if so, then I would say then the rest of the world, they have to measure it properly, because then if you know the origin, then you know the age, and if you know the age, you can place it properly into the evolution over time. So that means our concept needs to be made public to the others, and then let's see, maybe with some more measurements in terms of validating the geological background, we could possibly increase the fingerprint precision and then accuracy for this method.
So actually what we are doing is like criminology. We have some artifacts left from something that happened in the past, like in a crime scene. We're going back and taking the samples, and we go into the trace elements, into a world that's not visible for the people, but very significant. And then we measure them, map them, and we have like, these are not hairs now, these are samples, and these are not particles from clothes, but these are minerals. And the nature made it, and it's not a crime, but it's an event, and it's past, and we haven't seen it, and now we are in the criminology, analogy, but applied to geology. And each of the samples then has to be visited and studied and created data. And it's like fingerprint, but it's not from the hand. It's like a fingerprint from the nature that it implied by the interaction of this vein in the rock. And then we are using this criminology concept of measuring this mineral and apply it for the question whether the people that have studied these life forms in amber have been enough careful about the mix-up of the samples in the marketplace and whether they are really know the age of the samples and have not made a mistake. And so we're giving them a new test that they have to go back and check it out. And so it's like eventually everybody has to go and measure their veins at the end, and to if they are really interested and really want to know whether they are not making a mistake or not, because
it could well be that they all have to measure the samples, but in the first instance I have been involved in the crime scenery because yes, the method is possible for crime sceneries, so that more beautiful to work on real samples than on crime sceneries. But just aside, we have a proof of concept from more than 90 elements. We have 1 or 2 actually as indicators at the moment.
Mm-hmm.
So if we justify the method with some more samples,
mm-hmm.
then I'm 100% sure then the others have to remeasure their sample to put this into the logical time frame. And for that actually we have to do a little bit more homework. Proof of concept is shown, and then let's see how much and how good we can really determine the fingerprint background in terms of the different elements. And then it could become a new method for testing age and location.
Because we have to remember that there is a website that summarizes all the research that's done on the Burmese amber, and it lists all the new species that are found, and they are right now at 800. And there is a lot of interpretation whether the fossils actually evolution of some insects, spiders, pseudoscorpions, lizards and so on comes from Gondwana land, which is very much in the south during the Cretaceous, but later on it was not. And then it's Florasia. So if these models of how the animals propagated on the world and where they were formed first has to be very carefully put in the correct time frame, otherwise we are just ending up with a continent that is much more north, and then the theory that that insect or lizard was formed in Gondwana land much in the south and then propagated is just wrong. So it has huge implications for paleontology.
That's true, but you should not forget actually that a lot of misinterpretations have been made in the past, right?
Sample?
And technology development helped to put them into right perspective and to correct those things, right?
Right.
Now
so it's a normal process.
It is a very normal process. However, now it depends on the honesty of the owner of certain samples or the claims made actually. If there's really a new method and they are interested in contributing to the origin of life, then they remeasure and try to get actually as much as possible accurate data to bring the evidence where it's coming from and then the correct age.
I see it slightly different, because you were right in one point, but the other point is all these publications have holotypes. That means if they find something new species, they deposit it as a holotype in a museum. And actually I can go back to the sample and ask that I want to analyzing these calcite veins and redo it. I can ask, if they say no, it would be not a good sign for cooperating and finding the truth. So they have to be very careful on not saying no. But I can go back to all this work from all over the world and write everyone a letter and say, we have a new method and we need to revisit your sample and check whether there's a calcite vein, and then we want to measure it. So I can travel there, look the sample, if there's a calcite vein, I can make a proposal for an MOU or a loaning contract and go and measure it myself, right?
That's true, but I agree 100%. For the sake of accuracy and for the sake of evolution, you can do it for some species, but you should not tackle it as the world police to correct the others. It's more like bringing and shading new light into the entire paleontology by introducing this method. So it means coming from the curiosity side, it's better than coming from the police side. Even
I know
you put it into the crime scenery. You know what I mean?
No, I don't want to be misunderstood. I don't want to correct them. I want to know what it is.
Exactly. Your curiosity is the driving force.
Yeah, I don't want to correct them. I want to just, because when I want to interpret my new species, I find, and we have already 3 holotypes here in the museum, and then I have to put them into perspective of all the other publications. I'm forced to do so. And then sometimes there come results that doesn't make sense.
There are a lot of results which doesn't make sense.
Yeah, but I mean, I have to go back.
This was just a joke. I meant actually, you're right, and I'm completely on your side. You want to see if our method occurs as a calcite in the samples which you have at different locations, and if, then we can further and further validate that the trace elements we determine in the calcite or our indicator elements is really a method, and then we can start to look into the evolution and could say this one has been possibly
younger,
later,
older,
or younger.
Right, and then to correct it and correct.
Cool. That means actually this seems to be a project till the end of my scientific career and far into my pension. Thank you.
All right.
Cut.